Welcome, my people, to today's lesson. And we are continuing with chemistry, the second half of chemistry, destroying the JAMB 2026 syllabus. All right. So our topic for today is types of heat change. Okay. This thing you see like angle here is called delta, and it stands for what? Change. Then this H you see here stands for what? Heat. All right. So heat change, types of heat changes. All right. So that's that for that. So get your pen and your notebook to jot down whatever you understand in this lecture. Remember, I have a last-minute plan that can help you pass your JAMB UTME, even though you have not been preparing. Even though it is now you want to start preparing, even though it's 2 weeks you have left to prepare for your JAMB UTME, I can still make a difference in your JAMB score. I can still make you score 200 at least. I can even make you score 250, even though you have 2 weeks to prepare for your JAMB UTME. It's just basically strategy. It's something easy to do. There are things you have to concentrate on. There are fat investments and there are frivolous investments. All you have to do is to what? To ignore the frivolous investments and embrace the fat investments. Fat investments always comes with what? Fat returns. All right. So let's continue with what we have here on the screen. All right. Types of heat change. Okay. Physical process and chemical process. First of all, we have to understand these two processes. They both are so easy. Okay, I already explained what the physical process is while I was treating inorganic chemistry. Okay, because we are getting closer and closer to organic chemistry. All right. So while I was treating inorganic chemistry, while we treated inorganic chemistry, we discussed physical change and chemical change, or physical process and chemical process. Okay. Then for physical process involves process like melting, vaporization, sublimation. Here we all know these are separation techniques. Now melting. Sublimation is a separation technique. Okay, melting is a change of state. Vaporization is also a change of state. All right. So vaporization is when liquid turns to what? To gas. All right. It turns to what? Gas. Okay. So melting is when solid turns to what? Liquid. Okay. At melting point. Don't forget that. Always put that at what? Melting point. Okay. Then for physical processes are physical. They occur physically. It's based on what you see. Okay. And another thing, no new substance what is formed during a physical process. No new substance is what form. Okay, the substance remains the same. Only what changes is the state. In physical processes, only the state changes. All right, the substance itself doesn't change. The state of the substance can change. All right, maybe from solid to liquid, from liquid to gas, or from solid to gas directly. That's sublimation. An example of substance that possesses this sublimation is iodine and some volatile salts. And these three physical processes, they are all endothermic. They are all what? Endothermic. What does it mean that a reaction is endothermic or a process is endothermic? It means that the heat change is greater than zero. That's heat is required. Heat is required to what? To enable this, these physical processes. You need to heat them up before these physical processes will occur. So heat is required. That's endo. That's heat inside. Put heat inside. All right. Put heat inside. So for the process to occur smoothly, heat is required. So for these three processes like melting, vaporization, sublimation, heat is usually required. That's why change in heat is greater than zero. Okay, change in heat greater than zero. All right. Then for physical processes like freezing, that's when liquid turns to solid. Okay, that's freezing. Then condensation. All right, that's when gas is condensed. Okay, gas returns back to liquid. All right, so that's condensation. For these two processes like freezing and condensation, is an exothermic process. And as such, since it's an exothermic process, exo stands for giving out. That's heat is giving out. Heat leaves. Exo out. Heat must go out for the process to what? Occur. All right. So heat change will be what? Less than zero. Okay. So because heat needs to leave the system for the process to occur, or for this physical process to occur, heat change will be less than zero. All right. So for endothermic process, heat change is greater than zero because heat is required. But for exothermic process, heat change is less than zero because heat is not what? Required. All right, let's move over to the chemical processes. We all know what a chemical process is. A chemical process is a process whereby new substance are what? Formed. All right, new substance are what? Formed. There can be what? Exchange of what? Electron. Okay, or there can be share of electron. Either exchange or share of electron. All right, the share electron or donate electron or gain electron. Electron loss, electron gain, or electron shared. Okay, that's a chemical process. Okay, and the first list of chemical process for exothermic process here is combustion, neutralization. All these are exothermic process. Heat needs to be released into the surrounding. That's why when substances burn, they burn with heat, a lot of heat, because heat, the energy in the system is greater than the energy in the atmosphere. That's why the heat has to be evolved for the chemical process to occur, for the reaction to be completed. Hope you understood. All right. So combustion is an exothermic process. Heat is given off. All right, because the heat inside the system of the reactant is greater than the heat in the atmosphere. All right, so exothermic process, neutralization and combustion. All right. So another chemical process which is endothermic, that's heat is required, is photosynthesis. When plants utilizes what's it called, carbon 4 oxide to split water molecule and to reduce carbon 4 oxide. All right, so such process is a chemical process. Energy is required. That's why plant absorbs energy from the sun, all right, to carry out this process. And another one again, decomposition of a substance is just like melting a substance so that or heating up a substance so that it releases its constituents. So when you heat up a substance to release its constituents, all right. For example, when you heat up calcium hydrogen triazocarbonate 5, okay, you try to decompose it. It's going to decompose. It's going to break down dissociate, scatter, and yield its components. All right. Firstly, you are going to get the insoluble calcium triazocarbonate 5, and you are going to get carbon 4 oxide, and you are going to get water. Okay, decomposition. Let's look at the graphical representation of the heat curve. Okay, representing heat. Okay, heat of reaction. Okay, graphically, we use the heat curve. All right, to represent the heat of reaction graphically. Okay, the heat curve shows temperature versus heat added. The temperature of the system versus the heat added. Plateaus is equal to phase change. All right. Constant, and the phase change is what? Is constant temperature and change in heat absorbed / release. So change in heat is either the heat absorbed or the heat what? Release. What's the meaning of plateau? Plateau is a time frame, okay, where no change occur, okay, where no change will occur. It's like a dormant or a latent phase, all right, a latent phase, all right. Then the energy profile diagram is also another way to present, you know, the heat change during the chemical reaction, all right, and it shows enthalpy change in the reaction, which is the enthalpy change in the reaction is the heat change, all right. So when the reaction is exothermic, the product is lower than the reactant, or the heat of the product is lower than the heat of the reactant. Exothermic, heat needs to go out. Okay, that's why the heat of the product, for the product side, the heat within them will high. Okay, why for the reactant side, the heat within them will low. So such is an what? Is an exothermic reaction. Then for endothermic reaction, remember endo, heat is needed. Put heat inside, endo inside. Okay, so for endothermic reaction, the heat of the product will now be what? Will now be higher than the heat of the what? The reactant. So for endothermic reaction, the heat of the product will now be higher than the heat of the reactant, something like this. So this is an endothermic reaction. So anytime the heat of the reactant is lower, okay, just know that it's endothermic reaction, okay. But anytime the heat of the product, just use that one as a guide. Anytime the heat of the reactant is lower, just know that it's an endothermic reaction. The opposite will be vice versa for exothermic. All right. Now let's look at the heat curve and the energy profile diagrams. Let's look at the heat curve first. This is the heat curve diagram, okay? A graphical representation of temperature plotted against heat added. Temperature what in degrees Celsius plotted against heat added. Temperature on the y-axis, heat added on the what? The x-axis. All right, this is the heat curve, and you can see the curve. This is solid state. From here, is still in solid state, and you can see how straight it is. From here, it's climbing. Now it's straight. All right, it's straight. So I taught you that plateau is a phase where no change occur. So you can see that's why it's straight like this. Nothing occurred there. So it's from this place, this point, it transition into liquid. Can you see how it climbs? Can you see the slope? It climbs, transition into liquid, and from liquid, this same substance at this temperature, as at 100 degrees Celsius, that was when it was able to completely turn into a completely transition into liquid. All right. So it happened gradually as the temperature continued to increase. As the temperature continued to increase, here stands for heat added. The heat added and the temperature in turn in the system. All right. So you can see another plateau here again. Okay. A phase where no change occur. You can see it, plateau, a latent stage. All right. So from this plateau, it turns towards gas. Okay, at greater than what? 100 degrees Celsius. All right. This is the heat curve. This is the what? The heat curve. Now let's look at the energy profile diagram. This is one of the energy profile diagrams. All right, and this signifies an exothermic reaction. Remember, when you hear exo, that's heat is given off. That means that the reactant heat is greater than the product heat, because heat is given out. So we just use the reactant as a preamble. When the reactant is higher than the product, just know that it's exo. But when the reactant can't go inside, products can't go up. Okay, just know that it's endo. All right. So this one, that the reactant, can you see it, is higher than the product. Okay, so this exothermic reaction. When the reactant is lower, then this product go up, which we are going to look at very soon. Just know that the reaction is an endothermic reaction, all right, or an endothermic process. All right. So on the left side of the graph, or on the y-axis, we have potential energy. That's the energy in the system. While on the x-axis, or the horizontal axis of the graph, we have reaction process. Okay, what occurs in the reaction? So you can see the activation energy. So from here to here signify the energy loss. Okay, during the reaction. The energy what? Loss during the reaction. That's the what? The heat change, or the energy change. All right, the energy change. All right. So from here to here, this place where they curve like this. From measure the reactant. Okay, measure the reactant from the reactant to the reactant to the top. Okay, the highest, the highest distance of displacement. Okay, just like amplitude in wave. Okay, from here to here to here is the activation energy. Is the what? Activation energy. And what is activation energy? Activation energy is the energy required to activate the reaction, to start up the reaction. The energy required to establish the chemical process. That's activation energy. As easy as that. Easy peasy. Now let's look at endothermic reaction. Okay, this is an endothermic reaction, plotting the same thing. The difference is that I said when the reactants go inside, products can't go up. See, reactants now don't fall inside. You see how it fall inside? It's lower. Product is higher. Then it's an endo. Always remember, when the reactants fall inside, products go up. Endo, inside, endothermic reaction. Then you can see the activation energy, how high the activation energy is, because the reactants don't fall, go inside. Okay, the reactant don't fall, go inside. So you can see. So you measure the activation energy from the reactant to the maximum distance of displacement, which is this curve here up. That's how you measure the activation energy. If you look at the one for exothermic reaction, you can see that we started from the reactant to measure. Can you see? From reactant to the maximum distance of displacement. So from here to here is the activation energy. But see this one. You can see how long the activation energy is, how high it is, okay? The potential energy, very high for activation. That tells you that it's an endothermic reaction. Heat needs to be absorbed, okay? That's why the activation energy is high. To activate the reaction, you need a lot of heat energy to activate the reaction, okay? So the overall energy change is the energy required to convert from reactants to products, and that's it, from here to here, from here to here, okay? That's the overall energy change. Beautiful. All right, let's now look at physical state and orderliness. Physical state and orderliness. Solids, they are highly ordered. That's, the solids are highly ordered. Their molecules, they move slowly. Okay, the molecules inside the solid, it moves slowly because they are tightly packed. Okay, they are tightly packed, so no movement. Okay, no what? Movement. Okay, so that's why they are highly ordered. Scattered, they don't scatter. There's orderliness in solid, highly ordered. Okay, so that shows that it has low entropy. Entropy is the degree of scatteredness. Entropy is the degree of disorderliness in a what? In a chemical system. Okay, disorderliness, scattered. This one jam, this one collision. Wait. And remember, collision is required for a chemical reaction to occur. So entropy is required. You need a balance between the entropy and the enthalpy, okay, for a reaction to occur. All right. The Gibbs free energy is also there, but you need a balance between these two, okay, for a what? A reaction, a chemical reaction to take place. So solids have what? Low entropy, low degree of scatteredness. I just told you why. They are ordered, okay? They are ordered. Why in solids, their molecules are, they don't move easily. It doesn't have mobile molecules. Their molecules are tightly packed, okay? They're jam packed, so they don't even move freely. All right. So liquid has a moderately ordered. So liquid are moderately ordered because liquids, the molecule in a liquid are free to move to some extent. That's why they are moderately what? Ordered. They're not too, the entropy is not high. It's not so high, okay? It's not so high in liquid, okay? But it's moderate, okay? That's why liquid, you can pour liquid from here to here. You can transfer liquid from here to here because the molecules can move, all right? So for gases, now gases can't get the worst entropy because gases molecules moves freely. Their molecules do what? They move freely. So that's why if you open gas for that, no, I don't perceive for here because their molecules, they move. When you put gas inside a cylinder, the molecules of the gas is constantly bombarding the cylinder or the container of the gas 247 that they bombard because they are spaced apart. Their molecules are what? Are spaced apart. They have a high intermolecular space. You understand? The intermolecular space of the gases molecule are wide apart. Okay, it's very high. The space is very what? It's very high. All right. So gases has the least orderliness. So they are not ordered. Okay, they are not ordered. That's why they now have high entropy. That's high scattering in blue view. Okay. Disorderliness, okay, disorderliness. Gas, very, very disordered. All right. Let's look at the condition for spontaneity. That's when you say spontaneity of reaction. Okay. When you say spontaneity, it means that the reaction does not need any artificial, facilitator to allow the reaction occur. The reaction just occurs on its own. Nobody need to pull hand, may occur. It will occur on its own. It's just like you carry potassium, you put them inside cold water. Nobody, you don't need to facilitate them. It will just react explosively. What's going to be formed? An alkali is going to be formed. All right, but it's an explosive process, okay, because potassium is very reactive. All right, so a reaction is spontaneous if Gibbs free energy change, which is change in G, capital letter G, is negative. So the reaction is spontaneous when the Gibbs free energy change in G is negative. So when this energy is negative, the reaction is spontaneous. Okay, that's, you didn't add any energy, no artificial facilitation is required. Okay, so the change in Gibbs energy depends on both enthalpy, which is heat change, and entropy, which is what? Disorderliness. Okay, so remember, heat change can cause disorderliness, or heat change can cause both orderliness and disorderliness. Okay, so that's it. So entropy is the degree of disorderliness or the degree of orderliness in a system. All right, depending on the angle that you are looking at it from. All right, the degree of orderliness or disorderliness in a system, depending on the angle you are looking at it from. All right, so but the most common definition is the degree of disorderliness in a chemical process. All right, and it's required for reactions to occur. Required. Therefore, change in G, which is change in Gibbs free energy, is equal to what? Change in heat minus temperature and change in what? Entropy. Minus temperature times change in what? Entropy. Easy as that. JAMB, they like the set question from all these parts. They like all these parts. Let's now look at the relationship between change in heat, change in entropy, and change in Gibbs energy. All right. First of all, we are looking at driving forces of reaction, driving forces of chemical processes. What are the driving forces? What brings about chemical processes? What needs to be, put in place for a chemical process to occur, okay, to facilitate a chemical process, all right? The first here is change in what? Heat, which is enthalpy, all right? And the enthalpy, energy, is either released or absorbed, okay? For a balanced enthalpy, it is either energy is released into the atmosphere or energy is absorbed from the atmosphere for a reaction to occur. That's the relationship. Now we're looking at a relationship between changing heat and changing entropy and, the Gibbs free energy. Why for the change in entropy, okay, disorder slash randomness, okay, disorder slash randomness, okay, so there need to be what? Disorder slash randomness or randomness in the system for a reaction to occur. like I said before, okay? Because when there is disorderliness and randomness in the system, it shows that the molecules are moving. And for the molecules to move, it facilitates what? Reaction, all right? The next we have here is the Gibbs free energy. And Gibbs free energy is a spontaneity indicator, okay? It shows if a reaction is spontaneous or if it's not. So for a spontaneous reaction, the Gibbs free energy is less than what? 0, all right? But for a reaction that is not spontaneous, the Gibbs free energy is what? Greater than 0, all right? So in other words, for a spontaneous reaction, Gibbs free energy is negative. So for a reaction that is not spontaneous, Gibbs free energy is what? Positive, all right? So let's look at the examples we have here. When change in heat is less than 0 and change in entropy is greater than 0, what happened? The reaction is always spontaneous. Because change in heat is less than 0. Okay, it's less than what? 0. That's heat needs to be what? Given out to the what? The environment. It's an exothermic reaction, and you can see that the entropy, which is the rate of disorderliness, is greater than 0. So this reaction is always spontaneous. Okay, you don't need any facilitation. Okay, so when change in heat is greater than 0, that's heat needs to be added to the system, and the change in entropy is less than 0. What happens? The disorderliness now is now low. Heat is required. The reaction is never spontaneous, because it requires heat and it requires disorderliness for the reaction to occur. So when change in heat is less than 0, that's telling us that heat will be given out into the environment. Okay, heat is not required for the reaction to occur. Then change in entropy is less than 0. That's no disorderliness here. What happens? Spontaneity at low temperature. That's spontaneity of the reaction will be achieved at what? At a low temperature. Okay, because heat is given out to the surrounding. So okay, so at a low temperature is going to favor the reaction. All right. The final one we have here is change in heat. When change in heat is greater than 0, that's heat is required to be added into the system for the reaction to occur. You need to absorb heat for the environment. That's why change in heat is greater than 0. Then change in entropy is also greater than 0. What do you expect? What do you expect? You need heat. So that tells you that high temperature will what? Favor the reaction. That's high temperature will lead to the spontaneity of the reaction, because heat has to be added. And change in entropy is greater than 0 too. Okay, so that shows that there's already disorderliness. All right, so there need to be balance between these three. Okay, for a reaction to occur, the Gibbs free energy, the change in heat, the change in Gibbs free energy, the change in heat, and the change of entropy, or the change in enthalpy and the change in entropy. Formula for solving problems involving heat. Okay, heat and spontaneity of reaction is very easy. It's very easy. It's just plus and minus, plus minus. Nothing there. It's so easy. I don't lie you. It's so easy. Let me teach you how to solve it. Let me teach you. Okay. For example, using the formula, change in Gibbs free energy is equal to change in enthalpy or heat change minus temperature times change in entropy or change in disorderliness. All right. So the example we have here, the parameters or the figure that was given to us is if change in heat is equal to minus 100 kilojoules, then change in entropy is equal to minus 200 joule per Kelvin. All right. Then temperature is equal to 300 Kelvin. Okay, they are not asking you what is the Gibbs free energy, or check if the reaction is what? Spontaneous. Okay, check if the reaction is what? Spontaneous. So remember how to know if a reaction is spontaneous using the Gibbs free energy. If the Gibbs free energy is negative, that shows that the reaction is spontaneous. That's when it's less than 0. Okay, when the figure gotten is less than 0, that means the reaction is spontaneous. But when it's greater than 0, it shows that the reaction is not a spontaneous reaction. All right. So change in Gibbs free energy minus 100. We are now substituting. Change in heat, we are substituting minus 100 minus bracket open temperature. Look at it, T 300 Kelvin. Look at it. That's what we have here. Minus, look at the minus here. Minus, we bring it down. Minus. Then what do we have next? Change in what? Entropy. This is the change in entropy. Look at it here. Okay. Change in S or delta S is equal to minus 200 joule per Kelvin. So it's easy. We have brought everything down. Okay. Remember that what we have here, we are going to use our temperature to times our change in entropy. All right. So to solve these brackets, we are not going to do three. That's why I always say that you have to take my lectures. Just reading only the notes. There are things you might not understand. So what we are going to do, we are going to times 300 by 200. Okay. When you times 300 times 200, what is it going to give you? What it gives you, you are going to minus. You are not going to use what you get from here. Okay. It's going to give you a figure without minus. You are going to use what you get from here. You are going to do minus 100,000 minus what you have here. That's going to give you your final answer. The answer will be in minus. I know that you'll be asking yourself, why do we have 100,000 here? Okay, instead of 100. Remember, the heat energy is given in joule. Okay, joule. And here we are having kilojoule. So to convert 100 kilojoule to joule, what do you have to do? You have to what? You have to times by 1,000. Okay, and that's why we're having 100,000 here. All right. So as easy as that. What you get from here, okay, from solving here, What you have to do is just times 300 times 200. 300 times 200 to get your answer. What you get here, you use 100 to minus, what you have here from this minus 100,000 to get your answer. All right, the answer will still end up, you still end up having a negative answer. So that shows when it's negative, Gibbs free energy is negative. Okay, so what does that mean? Is it spontaneous or not spontaneous? Drop it in the comment section. Let's look at the facts about Gibbs free energy. All right, when the Gibbs free energy is less than 0, that's negative Gibbs free energy, what happens? Okay, the process is spontaneous under the given condition. Yes, we already discussed that. The reaction can proceed without external input, no facilitator, no artificial input. It will work on its own naturally. Yes, for example, the combustion of fuels, rusting of irons, etc. Now you go to pull heat, make it for combust. You go to light fire for gen before it combust. No be as you start, you go start to the combust. The combust heat will enter the environment. Everywhere will be hot like fire because of the reaction will occur inside the gen. Because it's an exothermic reaction. So therefore, the Gibbs free energy will be less than 0. All right, it will be negative. All right. Still on the fact about Gibbs free energy. When the Gibbs free energy is not equal to 0, it's not equal to 0, equal to 0. The change in Gibbs free energy is not equal to 0. What happens? The system is at equilibrium. So when the change in Gibbs free energy is equal to 0, the system is what? At equilibrium, balance. The rate of forward reaction balance the rate of backward reaction. The system is at what? Equilibrium. All right. So no net change occurs. All right. Forward and reverse reaction balances each other at equilibrium. Okay, for example, a saturated solution where dissolution and crystallization occur at equal rates. A saturated solution whereby dissolution of solutes, dissolving of solutes, okay, and crystallization, that's formation of crystals, and the crystals are recovered from the system. Okay, it occurs at equal rate. So the system is at equilibrium. The chemical reaction, the chemical process is at equilibrium. The third one, okay, when Gibbs free energy is greater, remember we did less than 0, we did equal to 0, which is at equilibrium, equal to 0. Then now we are doing greater than 0. When Gibbs free energy is greater than 0, we've discussed this thing before, but make I just remind you. That means positive Gibbs free energy, that is plus. Okay, this indicates that the process is non-spontaneous under the given condition. Yes, it's not spontaneous when it's positive. That's heat need to be added. You need to facilitate it. You need to establish it yourself. Something has to establish the reaction. That's external energy is required. For example, the electrolysis of water. Okay, the electrolysis of water needs electrical energy input, a direct current. Okay, that's it. So when Gibbs free energy is greater than 0, just know that the Gibbs free energy is the energy of the reaction. Okay, it's the energy of the reaction. Okay, the energy of the reaction, is it greater? Is it less? Is it equal to 0? So you should be able to figure out answer in your JAMB UTME. Now that we have understood Gibbs free energy, the heat changes, types of heat change, the heat curve, the heat diagram, how to differentiate between exothermic and endothermic reaction, and so on and so forth. Let's now take some JAMB must repeat questions to further test the knowledge we've acquired so far and measure our readiness to produce this JAMB UTME 2026. JAMB must repeat questions. Question 225. Which of the following processes is endothermic? A. Combustion of methane. B. Neutralization of hydrochloric acid and sodium hydroxide. C. Melting of ice. D. Condensation of steam. What's the answer? Drop the answer in the comment section, my scholar. You study book now. Question 226. In an exothermic reaction, the enthalpy of the product is what? A. Greater than that of the reactants. B. Equal to that of the reactants. C. Less than that of the reactants. D. Unrelated to that of the reactants. What's the answer, my scholar? Drop the answer in the comment section. You sabi book now? Oh yeah, let's go. Question 227. Which of the following conditions favor spontaneity of a reaction? A. Blah 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 blah. B. Blah 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 blah. C. Blah 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 at low temperature. D. Blah 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 at high temperature. What's the answer? My scholar, I know you know the answer. Oh yeah, drop the answer in the comment section. Question 228. I know you are a scholar. I know you sabi book. I know you know the answer to this question even before I start reading itself. You already know the answer. Well, let's go. At equilibrium, the Gibbs free energy change, which is change in G, is what? A. Positive. B. Negative. C. 0. D. Cannot be determined. What's the answer? I know you know the answer. Drop the answer in the comment section, my scholars. Question 229. Which of the following correctly expresses the relationship between Gibbs free energy, enthalpy, and entropy? A. Is it this blah blah blah? B. Is it this blah blah blah? C. Is it this blah blah blah? D. Is it this blah blah blah? Which of them is correct? You know the correct answer, right? This is so easy peasy ABC D shit, you know. Drop the answer in the comment section, my scholar.